intermolecular forces. So these are the attractive and the repulsive forces which exist between two species, two particles, which can be atoms or molecules. These forces plays a very important role in deciding the state of a substance. The moment these forces becomes very strong, the state becomes solid. When they are of moderate type, it can be liquid, and when they are weaker, the substance becomes gaseous. And these forces are not including the forces which exist between atoms which forms the molecules. Remember, so we are not talking about the bonds which are the one which are responsible for making the atoms combine with each other to form molecular species. We are talking about the forces which exist between those molecular species, which is making what one molecule come closer to each other or go away from each other. Now these intermolecular forces together are called van der Waals forces. It's a tribute to the scientist van der Waals, who has actually helped us to give the correction in the ideal gas equation, which we'll be doing later on in this chapter. So all these forces are called van der Waals forces, and these forces include mainly the dispersion forces, dipole forces, dipole-induced dipole forces, and even hydrogen bonding, which is the strongest out of all the four. So let us take these forces one by one. Let us first take dispersion forces. Which are also called London forces. See, these are the forces which exists between two non-polar molecular species, which exists between two non-polar, that's most important, non-polar molecular species. See what, like, let me give an example between helium and xenon, between CCl4 and iodine, like between hydrogen, nitrogen, all these. Since in these examples, the molecular species involved are non-polar, that is why the forces which attractive forces which exist between them are called the dispersion forces or the van der Waals. It's one of the van der Waals forces. Now how they work is, see, whenever we have these non-polar molecular species, at certain point of a time, what happens is the electronic cloud in this particular molecular species gets distorted towards one side, and this results in the formation of instantaneous dipoles or temporary dipoles. Now these instantaneous dipoles therefore distorts the electronic clouds of the other such molecular species, and also results in what? They also induces polarity in them, and that is why what we get is this type of distortion of the electronic clouds of the neighboring molecular species, and as a result the forces of attraction which develops, this is called, see, here also we have instantaneous dipole, here also we have instantaneous dipoles. The forces of attraction developed between them are called dispersion forces or London forces. These are the weakest type of intermolecular forces we are having, and they mainly are the ones which exist between the non-polar molecular species, or like molecular like hydrogen, helium, xenon, etc. These forces are called London forces on the name of the German scientist Fritz London, and that is how they have been named London forces, and also called dispersion forces. Remember, these forces always are attractive, and these forces becomes more and more weaker with the increase in the distance between these two temporarily dipole molecular species, and their interactive energy their interactive energy is proportional to the sixth power of the, inversely proportional to the sixth power of the distance between them, between the molecular species. So greater is the distance, so lesser is the energy, or lesser is the strength of this bond, these forces. So that is what we call them dispersion forces, weakest intermolecular forces of attraction. The next category of forces are dipole-dipole forces. See, these are the forces which exist between polar molecular species. So you have done in the chemical bonding chapter, like we have HCl. Now, due to the difference of the electronegativity of the two atoms, already the more electronegative one acquires a delta negative charge and the lesser electronegative one acquires a delta positive charge. As a result, they have what permanent dipoles and dipole moments, which are actually in the direction from positive to negative side. Now, when such polar molecular species come closer to each other, what they develops a force of attraction which are called dipole-dipole interaction. So for this, the necessary condition is both these the engaging molecular species must have permanent dipoles in them. Like we can have HCl and chloroform, we can have HBr and HI, we can have like we can't expect CO2 to have this kind of dipole-dipole interaction with HCl. Not possible, because CO2 is a non-polar molecular species. Now again, these dipole-dipole forces are attractive forces, and these forces' strength is what inversely proportional to the sixth power of the distance between the interacting molecular species. So greater is the distance, the lesser are the these magnitude of these forces, weaker are these forces. So this is what we have dipole-dipole forces. The third type of intermolecular forces is the dipole-induced dipole forces. Now these are the forces which exist between a polar molecular species and a non-polar molecular species. See the difference here. One will be a polar molecular species and other will be a non-polar molecular species. Now the polar molecular species is already having a permanent dipole. Now its dipole distorts the electronic cloud of the other non-polar molecular species like xenon, and what induces dipole moment in this non-polar molecular species. So this becomes your permanent dipole and this becomes your what temporary dipole, instantaneous dipole, or the dipole which has been induced into it. So the forces of attraction which now develops between these two, like example I have given you HCl and xenon, we can have HBr and CCl4, we can have between iodine and what NO2 molecule. So these are the examples of what the one molecular species is having a permanent dipole which due to attractive forces induces the dipole moment in the non-polar molecular species, and the force of attraction which the two develops is called dipole-induced dipole forces. This is dipole, this is induced dipole. Now the interactive energy of these forces is inversely proportional to the sixth power of the distance between the molecular species. So again it's almost as strong as this one, but we definitely what we find is this decreases with the increase in the distance between the molecular species. Fine. Now the next type of intermolecular forces we have is the hydrogen bonding, which is the strongest of all the four types. We call it H bonding or hydrogen bonding. See, it only exists, we have already done this in the previous chapters. In the bonding we have done, We know it only exists when the H is bonded to either N or oxygen, nitrogen oxygen, or to fluorine. And due to these strong electronegative elements, what happens is that these hydrogen atoms becomes highly electron deficient. So they start attracting the electron pairs of the electronegative atoms of the other molecular species like this one, and that forces of attraction which they develop are called hydrogen bonding. These are very strong forces and their energy varies from 10 to 100 kilojoules per mole. So that's the magnitude these forces are having, and they are the one which makes the substances what change into a liquid state. Like we know, we have already done, water is a liquid whereas H2S is a gas. We know HF is a liquid whereas HCl is a gas. So all these sort of examples we already know about this.